Diffraction by a single slit. Diffraction by a single slit, locating the minima. We shine a light through a very narrow slit, 0.15 millimeter. We expecting we get a one light at this one, but actually this is the one we saw. This is we have a minimum dark on both sides. In the center is a bright spot. Okay. When we study this one, we see when a source here is shine a light through a slit, and we observe it through that angle at this place. It's not quite convenient for us to study it. So what we would like to is the parallel light shining on the slit, and it deflects at parallel light too. So in this way, we put the source on the focus plot of this lens. So after the lens, it becomes parallel, shine into the slit, and then it deflects, and we collect it at this point, at angle theta to the normal force.
This setup consists of a microwave emitter, a microwave receiver, and a bar graph display whose length is proportional to the intensity of the microwaves picked up by the receiver. We'll use it to show how a beam of microwaves is diffracted as it passes through a narrow slit. These two metal sheets are attached to the center of the board with a narrow gap between them. If the microwave receiver is swung through the area in front of the gap, the pattern of microwaves is quite wide. If the slit is widened, will the pattern of emerging microwaves become wider or narrower? The pattern narrows as the slit is widened. This slide has a set of narrow single slits which we can use to diffract a laser beam. We'll shine the beam through 3 different slits and observe the pattern on the screen. Here is the arrangement of laser, slit, and screen. Here is the laser spot with no slit in place. Here is the laser after passing through a 0.704 millimeter slit. Here's the laser spot after passing through a slit 0.352 millimeters wide. Here is the laser spot after passing through a slit 0.176 millimeters wide.
We'll shine the beam from this laser through a slit whose width can be varied by turning a screw. Here is the laser spot on the screen when the slit is open wider than the beam. We'll close the slit down part way. The laser spot now appears to spread out slightly. As we continue to narrow the slit, a pattern of bright and dark spots appears on the screen. When the slit is almost closed, the pattern spreads out so far it nearly disappears. As the slit is opened again, the spot narrows, and the pattern of bright and dark spots reappears. Light passing a thin wire is diffracted. We'll use a thin wire and a laser to show the pattern of bright and dark spots caused by the diffraction. Here is the setup of laser, wire, and screen. This is the laser spot on the screen with no wire in the beam. This is the diffraction pattern obtained on the screen when the wire is inserted.
Huygens principle. All points on the wavefront serve as point sources of spherical secondary wavelets. Now, this is a wavelength in sometime t equal to 0, and all points as a source of the secondary spherical wavelets. So the wave spread out. Okay. After delta t, this one, the wave become this wave become this, and after a time t, the new position of the wavefront will be that of a surface tangent to these secondary wavelengths. Now, this is secondary wavelengths, this is a tangent. So, Huygens principle allowed us to tell where a given wavefront will be at any time in the future if we know its present position. Intensity in single slit diffraction, qualitatively and quantitatively. We look at this single slit with a diffraction. We observe a point P, which is at angle theta to the central axis. Okay. We divided the single slit by n equal zone. So each zone with width delta x equal to a over n. When the n approached to infinity, the delta x approaches 0. And delta x is also the separation between two adjacent zones. Based on the Huygens principle, each zone can be treated as a source of secondary wavelets. The diffraction pattern on the viewing screen is formed by superposition of the wavelets from n zones. Now, we look at this one. This is a P, okay? At an arbitrary point P on the viewing screen, with an angle theta to the central axis, and the magnitude of the wavelets from all zones are the same, because the delta x, the width of each zone, are equal. But their phases are different, since they pass through different paths. You look at this, the two lines from neighbor answers, okay? They have paths different. Now look at this. We look at the angle theta, okay? This is the separation, this is lines from the adjacent zone. And the separation delta x equal to a over n, and approach to infinity. Okay, we do a perpendicular line, this one, dashed line. So after that, the two lines have the same path, and the bottom line have extra. So they have path different. This is the green one, the B. The B equal to what? B in this triangle equal to delta x sine theta. So when these two lines reach point P, they have phase difference. Okay. The phase difference, we convert the path difference into phase difference. We know that 1 lambda distance equal to 2 pi phase change. So delta phi is the path difference of the wavelets from two adjacent zones. Okay, they have both. Now, I will put them together. We wish to derive an expression for the intensity I theta of the pattern as a function of theta. That's the intensity is a function of theta. We find the answer by representing the individual wavelets EI arriving at point P from zone I, called EI, by a phasor, okay, and calculating the resulting phasor amplitude. That's the answer we want to find. Okay, this is we write it, the E electric field at point P angle theta is equal to sigma OEI. This EI is the wavelet electric field arriving from P from zone I. Okay, this is integration actually. From above analysis, at any point P on the viewing screens, two faces from adjacent zones will have a same magnitude but different faces. And the phase difference is for two adjacent zones is delta phi 2 pi over lambda delta x sine theta, which is depends on the location of theta. Okay. Now this is the phase difference between adjacent zones. Okay. If we look at P, which is theta equals 0, that means it's on the central axis. Then we will find delta phi is 0. Okay, they don't have phase difference. So when in the central, see each phaser from every zone, they have the same phase. Okay, so they phase put together. This is the E0. Okay, which you can see is the maximum, no more than that one. It's maximum EM. So at the central is always maximum EM. Now, if we deviate, increase the theta, change the angle, we have a delta phi. And then we see this is each adjacent zone have a phase difference. They're the same. Okay? They're the same. This is one. Okay. So we put them together and we find the resultant E. This is the intensity at angle theta, which is smaller than this one. What is this one? This one equal to E maximum. Okay. And we will find this E theta. Now, if we increase the theta again, okay, we go further aside. Before we do that, we have new concept. This is the first phaser's phase. This is the last phaser phase. So the change, the difference frame, they call it this phi equal to 2 pi lambda A sine theta. Okay, the phi is the phase difference in radius between the top and bottom rays from the slit from A. So this is A sine theta instead of delta x. Phi is the phase difference between the top and the bottom line from the slit. And we see that if the delta phi further, we increase the theta, delta phi get increased. Okay, the phase difference between adjacent phaser increase, and at some point we can get this one. This one is this point overlap with this one. In other words, this phi is 2 pi. Okay, in this case, E theta is 0. We see nothing. This is a minimum. Okay, and if we further increase the theta, we can have this kind of situation, one round and more, so we can get another maximum. All right. So this explanation. Now we look at this phase. At the center is always maximum because from all section they don't have a phase change difference. They are put together. You get a maximum E theta. And then we move a little bit, increase the theta. We find delta phi increase, and we put this phaser together. We get this to E theta. This is smaller than this one. This is the point. Okay, and then we increase the delta phi theta, delta phi. So at some point, this is E theta 0. You get this as a first minimum. And then when delta phi again, so we can get another point, look like the smaller maximum, and so on. Let's see, calculate E theta. Now, we do R and R perpendicular to this phaser. This is the E theta we have to calculate. Okay, this is a small phaser, and this phi is the phase difference between the top and the bottom line. Okay, and we see the E theta from here is 2. This one. This one is R half theta. Now look at this. This is rectangular. This is rectangular. So this phi equal to this phi. This angle is half phi. So E0 is equal to 2 Each one is r sine half phi. Okay? Right. And the phi, you can like, this is phi, this angle is phi. This angle phi is equal to E maximum divided by r from this. This is angle is arc divided by radius r. So the r equal to E over phi. We put this r inside, we get E theta equal to 2 E over phi over c. And we put these two to the denominator, we get E0 equal to E maximum sine half phi over half phi. And we let alpha equal to half phi, we can rewrite this one as sine alpha over alpha. Alpha equal to 7 phi. Remember, the intensity is proportional to E squared. The arrow marked E0 corresponds to the amplitude of the wave disturbance and not to the intensity. Intensity proportional to the square. So we can conclusion. The intensity of light when we absorb from angle theta equal to maximum in the center sine alpha over alpha squared. This is the formula. Okay. This alpha equal to half phi. You know phi? Phi is a sine theta transferred to 2 pi over lambda. Okay? Now, so we put it inside. So the alpha equal to pi over lambda a sine theta. Okay? Now, I maximum is the greatest value of the intensity, I theta, in the pattern. And it always occurs at the central maximum, where theta equal to 0. Because theta equal to 0, alpha equal to 0, sine alpha or alpha limit equal to 1. Okay? Equal to 1. And then to the minimum. The minimum is sine alpha equal to 0. This is not equal to 0. So we get alpha equal to alpha. This is alpha. Equal to what? Equal to m pi. When it's equal to m pi, sine m pi equal to 0. M could be 1, cannot be 0. 0 is the central, is maximum. Okay. So n may be 1, 2, 3, 4, and so on. This is minimum. Now, look at this formula. We cancel the pi and move the lambda here. When minimum happen, means a sine theta equals m lambda. This is the minimum formula. Okay. M can be 1, 2, 3, 4, not 0, because 0, theta to 0 is always the maximum. Diffraction by single slit. This is the minimum condition. M equal to 1, 2, 3, 4. Okay. And we can find the theta. Okay, find the theta. In a single slit diffraction, dark fringe, this is dark fringe, are produced where the path length difference, a sine theta, between the top and the bottom rays are equal to lambda, 2 lambda, 3 lambda. And at the center where theta equal to 0, it is always maximum. Now, this is a plot from our calculation. Okay, this is the picture we can take. Now, this is central is always maximum. This is the first minimum. We see dark. This is dark. This is the second minimum. Okay. Yeah. The dark is a sine theta equals m lambda. M equal to 1 is the first minimum. Okay. Yeah. This m equal to 2, second minimum. Both sides is symmetry. Okay. If you look at this one, is the narrow slit is narrower, a small it is smaller, then this is the same, 1 lambda, so this should be larger. And that means that means it's spread. Now, this is spread. Okay. Why the angle is larger, spread. It can be further spread. We can hold something. Wave flares out. Now look at this. If we have a lambda shining almost at the magnitude at the width at the A, here A is about 6.0 lambda, and then we see it's flared out. If we narrow in the A is 3.0 lambda, you see it flares out. And if A is continues smaller, 1.5 lambda, it gets larger spread out. Example, a slit with A is illuminated by white light, which consists of all wavelengths in visible range. Question A. For what value of A will the first minimum for red line of wavelength lambda 650 nanometer appear at theta equals 15 degrees? This is very simple. We just have a formula, we put the number inside. Okay, what do we want? We find the A. We have angle theta 15 degrees, and this is the first minimum. So m equal to 1, lambda equal to 650 nanometer. So we find A. Very simple. A is 2.5 micrometer. Question B. What is the wavelength lambda prime of the light whose first side diffraction maximum is at 15 degrees? Thus coincide with the first minimum for the red line. We have the formula for minimum. The maximum is between two minimum. So maximum formula is not m lambda, that's m plus half. M. So 1.5 is the first side maximum. Central maximum, first minimum. 1 is first minimum. 1.5 is first maximum. 2 is second minimum. 2.5 is second maximum. Yes. So now we know this is a 15. Okay. We know A, so we can find the lambda prime. That's very easy, tedious work. Okay. Yeah. And put A is 2,500 nanometer. Theta is 15. This is 1.5 with the lambda. Okay. Sample. Find the intensities of the first three secondary maxima, the side maxima, in the single slit diffraction pattern of the figure, measured relative to the intensity of the central maximum. We want to find the first side maximum, first maximum, second maximum, third maximum, relative to the central maximum. Now, we know that the formula, the alpha must be n plus half pi. Then we put the formula, we get the maximum. Okay? If this m pi, then it's minimum. So the intensity I m to the I central in this one by formula. Okay? And this one must be 1. So it will be m plus half pi. You can get the 1 maximum. Right? Now let's see this one. We put this one inside. We put m equal to 1, the first maximum. Okay. So the first maximum to the central maximum, we put it is 1 plus half, was it 3 over 2 pi. 3 over 2 pi, we can get the percentage. Okay, at 4.5. And the second m equal to 2, this is a 5 pi over 2 over 5 pi over 2, 1.6%. And then put this into 3, this is 7 over 2 pi, get a point. So we see that the secondary successive maximum decreases rapidly in intensity, 1 to 4.5, then to 1.6, then to 0.65. It's very